Today I am going to update the playlist of my channel called Classical Mechanics. You know that the playlist of Classical Mechanics of my channel does not contain a very important chapter of classical mechanics, which is dynamics of a rigid body. So many viewers of my channel have demanded to provide videos on the chapter dynamics of rigid body. So today I have started to provide the videos on this very important chapter. Actually, in first few videos we will learn the basic facts or basic fundamentals of this chapter, and after that we will start the real theories, the real concept of the dynamics of rigid body. I think you have an idea of rigid body. You have earlier also studied the concept of rigid body, and you know what is this rigid body. When we talk about a rigid body, actually this is just a system of particles in which the distance between any two particles does not change throughout the motion. The body may perform any type of motion, that may be a translatory motion, that may be a rotatory motion, or a combination of both. But during that motion, if the distance between any two particles of the body does not change, that remains constant, then you may call that body a rigid body. In other words, you can also say that the distance between the two particles, as you can see this figure, I have considered two particles which are ith and jth particle, and I have marked that this Rij is the distance between these two particles, okay, of a rigid body. So regardless the forces acting on this body, this distance Rij will not change, okay. So actually the body which satisfies this constant of motion during its motion, such a body is called rigid body, okay. So if you consider that there is a system of n particles, okay, and this system of n particles will be called a rigid body if it is subjected to a holonomic constant of this form Rij, which is actually the distance between ith and jth particle, is equal to Cij, where Cij is a constant. I hope you can remember the concept of holonomic constant. I have actually discussed this holonomic constant in my previous video in Lagrangian formulation in very detail. When actually, you know, the constant or the condition is imposed on the position of particle, then the constant is called holonomic. And you can see in this case the constant is imposed on the position of particles, because in case of rigid body we simply say that the body is called rigid only when the distance between any two particles of the body remains constant during its motion, or irrespective of the forces acting on the body, okay. Actually one can think that when a rigid body is in motion, then the deformations may occur. Body may change its shape, and when the shape will change, then one can think that the distance between two particles may change. So actually in the theory of rigid body, in accordance with its definition, we neglect the deformation of the body, okay, and we consider that the shape of the body does not change, it remains same whenever the body is in motion. This is just an ideal situation. Actually when deformation will take place, definitely the distance between 2 points or 2 particles of a rigid body will change, but we neglect for a time being for the discussion of motion of the rigid body, okay. So what is a rigid body? I think now you have understand. Okay. Now, actually, in this first lecture on this rigid body dynamics, we are going to see the concept of generalized coordinates of a rigid body. You know, in classical mechanics, whenever you talk about the motion of a system, that motion is determined, or that motion is described in terms of generalized coordinates. So if your aim is to discuss the general motion of a rigid body, definitely you should first of all know what will be the generalized coordinates of a rigid body. Okay. So let us now try to develop the concept to find the generalized coordinates of a rigid body. Okay. In fact, when you talk about generalized coordinates needed for the specification of a system or the motion of a system, then you have to think about the degree of freedom of the system. As you have learned in my lectures on Lagrangian formulation, what is degree of freedom, how we can find the the number of degree of freedom, and how we can determine the generalized coordinates. So if you can remember my previous video on Lagrangian formulation on a degree of freedom and generalized coordinates, then you can think that if a system consists of n particles, I have written here ordinary system. It means in that chapter we have not talked about rigid body, but we have considered a system of n particles where n particles were form actually a discrete system. Okay. So in that very ordinary system of particles containing the n particles, the degree of freedom f is given as 3n minus k. You know, you can remember. What is this k here? You know, k actually represents the number of equation of constants. Okay, these are number of equations of constants. So whenever you have to find the number of degree of freedom of a system containing n particles, then you have learned till now we can find that number of degree of freedom by utilizing this very formula, which is 3n minus k, where n represents the total number of particles of the system. But does this formula work in case of rigid body? Answer is no. In case of rigid body, this formula does not work well. It may fail. Why this formula fails in case of the motion of rigid body for finding the degree of freedom? Let us now try to understand this. So I have written why this formula does not work in case of a rigid body. Actually, if you consider that there are n particles in a system, then the maximum number of equations of constant is given as k equal to 1 over 2 n times n minus 1. This is the maximum number of equation of constant. Okay. And you know, this degree of freedom f must be greater or equal to 0. This must be positive. It means this degree of freedom is never negative, so it cannot be less than 0. And if this cannot be negative, in that condition you can say that this 3n must be greater or equal to k. It means this formula will be valid only in case when 3n is greater or equal to k. Or in other words, you can say that k is less or equal to 3n. Okay. Only then this formula will work. Okay. If k has such a value which is greater than this 3n, then this formula will not work, and k is given by this formula. So let us see some of the important examples here. If you consider that there is a system containing only one particle. So if we talk about a system of only one particle, then what will be this k? See here. n is equal to 1, so n minus 1, that is 1 minus 1, will be equal to 0. So in this case there will be no constant imposed on the system. So in case of a system of one particle, there is no constant imposed on the system, and that's why the degree of freedom will be simply equal to 3 times 1 minus 0, which is equal to 3. This is a well-known result. You know, a single particle has 3 degree of freedom, and all these 3 degree of freedom are translational degree of freedom. No rotational, no vibrational degree of freedom. Okay, you have learned these things in my earlier videos. Now, if we consider another simplest system containing 2 particles, it means you are taking n equal to 2. Then what will be k? Utilizing this formula, you can find the value of k, and that will be 1 over 2 times 2 times 1. n minus 1, that is 2 minus 1, that will be 1. And this 2 and this 2 will cancel, and so this will be 1. So in this case, the number of equation of constant is equal to 1. So what is degree of freedom? Utilize this formula, 3n minus k, that will be 3 times 2 minus 1, that is 5. So if a system contains 2 particles, then the number of constant imposed will be equal to 1, and degree of freedoms of such a system will be equal to 5. Actually, in this case, there may be 3 translational degree of freedom and 2 rotational degree of freedom. As we have learned, in case of diatomic molecules, such situation actually exists. Okay. If you consider that n equal to 3, then what will be degree of freedom? You can see in this condition the number of equations of constant will be equal to 3, and so that the degree of freedom will be 3 times 3 minus 3, that is 6. Okay. And in this case too, the degree of freedom may be a combination of translational degree of freedom and rotational degree of freedom, and it may be also a vibrational degree of freedom. Okay. Actually, here in these first 3 examples, you have seen that the degree of freedom comes out to be plus 3, plus 5, plus 6, and so on. And all are positive. So in this case, for all these 3 systems, this formula for finding the degree of freedom works well. But now let us take a system containing a large number of particles. For example, we can take n equal to 100. If you will take n equal to 100, then what will be k? The number of equations of constant k will be equal to 1 over 2 times 100 times 99. And that will be 4950. So in this case, if you will try to find the number of degree of freedom by utilizing this very formula, what will be your result? You can see this will be 3 into n. n is 100, so this is 3 into 100, and minus 4950, and that will be minus 4650. So you can see in this case this degree of freedom comes out to be negative. Does it possible? Answer is no, because degree of freedom is never negative. So you can see this formula f equal to 3n minus k for finding the number of degree of freedom fails badly when we consider a system containing 100 particles. And you can think that whenever we consider a rigid body, what is the number of particles in a rigid body? A countless number of particles is contained in a rigid body. So definitely this formula will completely fail in finding the degree of freedom of a rigid body. So I have told you earlier that this formula f equal to 3n minus k for finding the degree of freedom for an ordinary system does not work well in case of a rigid body. I think you have completely understand this explanation. Okay. So I have mentioned here that as f can never be negative, so the above formula fails when n is large. Okay. Now let us see when this formula will work well. As I have told you, for validity of this formula, this k should be less or equal to 3n, and k is equal to this much. This is n times n minus 1 over 2, and this should be less or equal to 3n. So this n and this n will cancel out, and you can say that n minus 1 must be less or equal to 6, and therefore n must be less or equal to 7. So this formula will hold only in case of a system containing at most 7 particles. If the number of particles contained in the system is more than 7, then you cannot find the number of degree of freedom utilizing that very formula. Okay? And in case of rigid body, the number of particles is not 8, not 9. It may be millions and millions. And so this formula F equal to 3n minus k does not work well in case of finding the degree of freedom of a rigid body. So we can say that in case of rigid body, n is very large, so F is not equal to 3n minus k. Okay? Actually, the equation of constant which you have actually written here, actually this equation, these are a large number of equation of constant. Actually these equation will contain are actually not independent of one another. Okay, so in fact the equations represented by that equation 1 are not all independent, and that's why we cannot find the number of degree of freedom utilizing this very formula. Okay, so what is a rigid body? Can you find the degree of freedom of a rigid body utilizing this formula F equal to 3n minus k? Can you find or not? I think you have clearly understand this idea. Okay. Now we are going to see what will be the degree of freedom of a rigid body. So remember, actually the number of degree of freedom for general motion of a rigid body is 6. You should remember it. This is a very important fact for your objective type question. So when a question will be asked what is the number of degree of freedom of a rigid body, and options are 6, 5, 4, 3, what will be the answer? Answer will be 6. Okay. When you say that the number of degree of freedom of a rigid body in case of its general motion is 6, what does it mean? It means you will need 6 independent variables or 6 independent coordinates for dealing the motion of the rigid body, and that coordinates or that independent variables are called generalized coordinates. So whenever we will have to discuss the motion of a rigid body, you must have 6 generalized coordinates. Okay, but how you can say that a rigid body will have 6 degree of freedom? Or to discuss or to describe the motion of a rigid body, we need 6 independent variables or 6 generalized coordinates. How you can say? Actually, this fact can be explained in 2 ways, and I am going to here discuss both of these ways how we can say that a rigid body has 6 degree of freedom. Okay, so now let us see first method to explain that the degree of freedom of a rigid body is 6. And for this you can see I have considered a rigid body here. This figure actually represents a rigid body. Okay, and we also consider that there are 3 non-collinear particles which I have marked by P1, P2 and P3. You can see the figure. Here P1, P2, P3, these are 3 particles and these are non-collinear. It means these 3 particles are not lying on the same line. They are lying at different lines. Okay. And each particle has 3 degree of freedom, because when you will specify the position of a particle with respect to an arbitrary origin, then you will assign 3 position coordinates for each particle. For example, if you are talking about the particle P1, the 3 coordinates are x1, y1 and z1. And similarly, in case for particle P2 and P3, these are x2, y2, z2, x3, y3 and z3. And as 3 independent variables are needed to describe the motion or the configuration of each particle, so we can say that each particle will have 3 degrees of freedom. Okay? And all these 3 degrees of freedom will be actually the translational degree of freedom. So as a whole, when you talk about the system of these 3 non-collinear particles, what will be the total number of degree of freedom? That will be simply 3 plus 3 plus 3, that is 9. So the total number of degree of freedom, if there is no constant present, if no constant is imposed on this system, in that condition, the total number of degree of freedom will be 9. Okay? But here, if these 3 particles are the particles of a rigid body, then there will be certainly constraints imposed on them. And what are the constraints? You know, in case of rigid body, you know the constant is the distance between any 2 particles remains constant, remains unchanged during its motion. So in this case, you can see we can write 3 equations of constant. I have marked here this R12. What is this R12? R12 is actually the separation of particle P1 and P2. Or you can say this R12 is the distance between particle P1 and P2. And similarly, R23 is the distance between particle P2 and P3. And R13 is the distance of particle P3 from P1. Okay? Or between P1 and P3. And you have definitely studied in your course on mathematics a very important chapter, coordinates, in coordinate geometry, where you learn about the distance formula. Okay? So utilizing the distance formula, you can find the values of R12, R23 and R13 if you know the coordinates of points P1, P2 and P3. And you know what is that formula? If you are going to find the value of R12, you know that will be given by a square root of x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. And if the body is rigid, you know this will be equal to a constant. And I have written that very constant by the symbol C12. Okay. Now again, the distance between particle 2 and 3, you can see the coordinates of point P2 is x2, y2, z2 and that of P3 is x3, y3, z3. So this distance R23 will be equal to a square root of x2 minus x3 square plus y2 minus y3 square plus z2 minus z3 square, and that will be equal to C23. Okay? And similarly, the distance between particle 1 and 3, that is given by this. So these are actually the 3 equations of constants. So you can say that in this case, if we consider a system of 3 non-collinear particles, then the number of equations of constant k is equal to 3. Okay, k is equal to 3. And so what will be the degree of freedom of this 3 particle system? You know the formula, F equal to 3n minus k. Okay, so this will be 3 times 3 minus 3 because number of particle is 3 and k is also 3. So this is equal to 6. So in this way you can see that if we consider that a system of 3 non-collinear particles of a rigid body, then the degree of freedom will be equal to 6. Okay. But one can think a rigid body does not contain only 3 particles. There may be a large number, there is a large number of particles in a rigid body. So now let us try to find if we consider any other particle except these three particles, then the degree of freedom increases or decreases. What will happen? Okay, and for this you can see I have shown in this figure uh, an arbitrary particle pi. Okay, you can say that this is fourth particle or fifth particle or any number of particle. Okay, and we will try to understand what will happen to the number of degree of freedom if we will consider this particle pi. Okay, if you consider that the coordinates of this point are xi, yi and zi. Okay, then with respect to point P1, the distance of point Pi is R1i. With respect to P2, its distance is R2i. And with respect to P3, its distance is R3i. And again, utilizing the distance formula, you can find this R1i, R2i and R3i. Okay? And you can see these will be R1i will be equal to a square root of x1 minus xi whole square plus y1 minus yi whole square plus z1 minus zi whole square, and that will be equal to a constant because that fourth particle is also of the same rigid body. Okay, and similarly this R2i will be equal to this much, and that is also a constant C2i, and similarly R3i is equal to this much, which is also equal to a constant C3i. So what you are observing here, you can see there are three equations of constants even when we consider any other particle apart from the three particles. Again, you have only three equations of constant. Okay, and therefore you can say that any other particle will not add any new degree of freedom to the 6th degree of freedom of this three particle system. Okay, so finally from this idea we can conclude that although a rigid body contains a very large number of particles, but its degree of freedom will be equal to 6. Okay, its degree of freedom will be equal to 6. So finally we conclude that F is equal to 6 for a rigid body. Okay, and if degree of freedom is 6, you know, then if your aim is to describe the motion of a rigid body, you must need 6 independent coordinates or 6 independent variables to specify its motion. Okay, so this was the first way to understand how we can say that the degree of freedom of a rigid body is equal to 6. Okay, now let us try to understand the same fact by another way. We will learn that the degree of freedom of a rigid body is 6, but our learning will be by another method. Okay, and for this let us consider the position of particle P1. If you consider the position of particle P1, can you say what will be the number of coordinates to specify its position? Definitely that will be 3, x, y, z. Okay, so to specify the position of particle P1, we will need 3 independent coordinates, and as the degree of freedom is equal to the number of independent coordinates, so you can say that the degree of freedom of particle P1 is F1, and that F1 will be equal to 3. Okay, now now see about the particle P2. Okay, and here there is particle P1. So with respect to this particle P1, with respect to or relative to particle P1, what will be the degree of freedom of this particle P2? As you know, relative to particle P1, the distance of P2 from P1, which will be R12, that is equal to constant. That will be equal to constant. Okay, so in this case there will be one equation of constant. This R12 equal to C12 is equation of constant. Okay, so for particle P2 there is one equation of constant. Okay, and so k is equal to 1. So in this case k is equal to 1. In first case k was 0, but here k is equal to 1. So in this condition, relative to particle P1, P2 will have the degree of freedom F2 equal to 3 minus 1, because there is one particle and that will have 3 degree of freedom in absence of any constant. But relative to P1, P2 has been imposed one constant. And what is that constant? That constant is distance of P2 from P1 is fixed. Okay, and so F2 is equal to 2. Okay, so P1 has 3 degree of freedom, P2 has 2 degree of freedom relative to P1. Now let us think about P3. Okay, when you talk about P3, okay, this is your P3, then there will be two equations of constant. Distance of P3 from P1 is fixed, distance of P3 from P2 is also fixed. So there will be two equations of constant. R13 is equal to C13, which is a constant, and R23 is equal to C23, which is also a constant. And so in this case, the number of equation of constants k is equal to 2. Okay. So what will be the degree of freedom of particle P3 relative to P1 and P2? That will be F3, and that F3 will be 3 minus 2, that is 1. So what you are looking here, you can see the degree of freedom of particle P1 is 3, degree of freedom of particle P2 relative to P1 is 2, and degree of freedom of particle P3 relative to P1 and P2 is 1. So in total, what is the total number of degree of freedom of this system of these three particles? That will be simply the sum of all these degree of freedom. So the total degree of freedom of the system of three particles, which is equivalent to degree of freedom of a rigid body, that will be equal to F1 plus F2 plus F3, and that is 3 plus 2 plus 1, which is equal to 6. Okay. So I think now it is clear to you by these two ways how we can say that a rigid body will have 6 degree of freedom. Okay. Now among these 6 degree of freedom, if the degree of freedom is 6, you know there will be 6 independent variables or 6 independent coordinates. And what will be those coordinates? Now let us try to think about it. And so first of all, see, let us consider the particle P2, motion of particle P2 relative to P1. Okay. If we talk about the motion of particle P2 relative to P1, we simply consider P1 located at the origin. And if the distance between P1 and P2 is fixed and P2 is moving with respect to P1, then definitely this P2 will move on the surface of a sphere. This is a sphere, and P2 is moving on the surface of this sphere relative to P1. Okay. And as if the particle P2 is at the surface of the sphere, there should be 3 coordinates, r, theta and phi. Okay. But since r here is the distance of P2 from P1, which is equal to radius of this sphere, and that is equal to R12, and that R12 is constant. So this R is not treated like a coordinate. So in this case, you can say that the motion of particle P2 relative to P1 will be described only in terms of theta and phi, these two angles of rotation. So for describing the motion of particle P2 relative to P1, we will need only two independent variables, and those independent variables are actually theta and phi, and these are actually angular coordinates. Okay, angular coordinate. So in this case, the generalized coordinates are theta and phi. You can see I have mentioned relative to particle P1, the particle P2 is constant to move on the surface of a sphere of radius r, which is equal to r12 equal to c12, and that is equal to constant. And therefore, its position is specified by the two angles theta and phi, and I have shown those two angles here. You know, this angle is theta, which is also called co-latitude of this place, and this is in fact phi, which is also called azimuthal angle. Okay, so in this case there are two generalized coordinates, and those generalized coordinates are actually angles, not they are not actually length. Okay, now let us see the motion of particle P3 with respect to P1 and P2. When you will talk about the motion of particle P3 with respect to P1 and P2, what type of motion P3 will perform? Actually, in this case, the particle P3 will rotate about an axis which is found by joining the position of particle P1 and P2. If you will join the position of particle P1 and P2, then P3 will rotate about this axis. And let us see, initially P3 was here, and at any time t it is at this position, and it has been rotated by this angle psi. Okay, so this psi will completely determine the motion of this particle P3 about relative to P1 and P2. So in this case, there is only one generalized coordinate, and that is also an angle of rotation, which is psi. Okay, so I have written it here that in this case there are two constant of equations, r13 equal to c13 and r23 equal to c23, and thus P3 is constant to rotate about the axis joining P1 and P2, which can be specified by the third angle of rotation marked by this psi. Okay, so what you can conclude, you can see that the rigid body has three translational and three rotational degree of freedom. Okay, these theta, phi and psi, these are three rotational coordinates, okay, or angular coordinates, which represents actually the rotational motion. And x, y, z, these are the position coordinate, which actually describes the translational motion. So you can say that in case of a rigid body, there are three translational degree of freedom and three rotational degree of freedom. Okay, and total there are 6 degree of freedom. Okay, so if your aim is to describe the motion of a rigid body, then usually you have to choose three coordinates of a point inside the rigid body. And the most convenient technique to decide a point inside the body, although point may be anywhere inside the body, but the most convenient is to take that very point whose three coordinates we will assign as the center of mass of the body. So in assigning the 6 independent variables, first of all, we consider or we take the coordinates of center of mass of the body, whose coordinates are capital X, capital Y and capital Z. And we also consider the three angles phi, theta and psi. Actually, we'll learn after some videos about the Euler's angle. Actually, these three angles are called Eulerian angles. Okay. So now you can say that the 6 generalized coordinates in case of rigid body are what? The 3 are the position coordinates x, y, z of center of mass of the body, and 3 are the angle of rotations, and those angle of rotations are marked by phi, theta and psi, which which are called Euler's angles. We will learn in very detail in our forthcoming lectures the idea of Euler's angle. Okay. So now you can see that these are the independent variables x, y, z and phi, theta, psi. So till now we have find there are 6 degree of freedom of a rigid body, but when you have find it, you have only imposed the constraint that the distance between any two particles of a rigid body is fixed. If we consider only this constraint, then you can say that a rigid body will have 6 degree of freedom. But what will happen actually when we impose extra constraint, other constraint? Actually, in addition to the constant of rigidity, if the body has additional constant, then this degree of freedom will further reduce. Okay, and if the degree of freedom will be further reduced, the number of independent variables or generalized coordinates to describe the motion of rigid body will also reduce. For example, here I have discussed a very important example. I have written that to find the number of degree of freedom of a rigid body which has one point fixed. Actually, this is a very important example. When in our forthcoming lecture we will learn about Euler's equation of motion, then you will see we will consider a rigid body which will be fixed at one point. So now let us try to find the number of degree of freedom of a rigid body when, apart from the constant of rigidity, we also impose a constant that the body is rigidly fixed at a point. Then what will be the number of degree of freedom? Okay. Actually, in this case, the motion of the rigid body is completely specified if we know the coordinates of 2 points. Let us say first point is P1 and another is P2, whose coordinates are x1, y1, z1 and x2, y2, z2. Okay. And the body is fixed at this point O, which is taken as origin. So its coordinates has been shown 0, 0 and 0. Okay. So in this case, you can see if you say that the distance of particle P1 from this origin or from this fixed point is R1O. Okay. And the distance of P2 is R2O. And distance of between P1 and P2 is R12. Okay. Then there will be, again you can see there will be 3 equations of constant. First of all, we will see. First of all, R10 will be equal to what? That will be x1 minus 0 square plus y1 minus 0 square plus z1 minus 0 square root. So this is simply a square root of x1 square plus y1 square plus z1 square, and that will be equal to constant. Similarly, R21 will be equal to a square root of x2 square plus y2 square plus z2 square, and that will be also a constant. Okay, and R12, this will be given as a square root of x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square, and that is equal to constant. At the first sight, one can think that we have 3 independent equations of constant, but actually in these 3 equations there are 6 variables, x1 x1 y1 z1 and x2 y2 z2. But are these 6 variables independent from one another? No. Actually, one can find among these 6 coordinates, you can find 3 coordinates, okay, in terms of the remaining 3. If you want to find the value of x1, y1, z1, you can find their values in terms of x2, y2, z2. So actually, among these 6 coordinates, all are not independent from one another, but only 3 coordinates are independent from one another. Okay. So in this case, you can say that the number of independent coordinates or independent variables when the rigid body is fixed at a point is equal to only 3, not 6. And as the number of degree of freedom is equal to number of independent variables or independent coordinates, so you can say if the rigid body is fixed at a point, then its degree of freedom will be equal to 3, not equal to 6. Okay. So I think you have understand how we can determine the degree of freedom of a rigid body when it is fixed at a point. This is a very important example, and you will see its utility in our forthcoming video. Okay. So this was a basic fact regarding the motion of a rigid body, and we will enjoy other videos which will be very important for you in our forthcoming lectures. Okay, thank you very much.